All right, folks, let's give this a try, see how well this works. This is going to be Physics 12, Determining Mass of Planets lesson. So let's go. Okay, so in using our formulas and all that good stuff that we talked about before with gravitational constants and stuff before the break, we are going to extend that and start looking at determining the mass of the sun and planets, right? How we can use those formulas to do that, how we can use Kepler's law to help us do this, as well as then also looking at some geostationary orbits and Newton's Cannon thought experiment as well, okay, which is a key aspect. So we'll start with determining large masses, right? So I mean, if we've ever seen that value of the mass of the Earth or any other planet, right, you kind of go, well, how on earth would we have ever weighed that, right? How do we get a mass for that? But how we actually do that is mathematically through a combination of the universal gravitational constant, which we had talked about before our break, as well as Kepler's third law, right? And we talked about Kepler's laws, about objects that actually orbit in a slightly elliptical pattern is not fully circular, as well as that for every equal unit of time, it breaks off an equal area of that kind of ellipse. It kind of shows as well that our objects are moving faster as they move closer towards the object that they're rotating around. And then our Kepler's third law, which was that idea that for all planets rotating around the same celestial body, right? So in our case, like all the planets in the solar system are revolving around the sun, we have that kind of constant where the period it takes for them to do a rotation, right? So t squared divided by the radius, or the distance between those two cubed, will always equal the same constant, okay? But again, that constant is only constant for if they're all revolving around the same body. Okay, so that's what we're gonna be looking at. So like I said, Kepler's third law, which is what you're seeing here, right? With that t squared over r cubed being a constant, or r cubed over t squared being a constant, it will essentially give you the same thing, just the constant will be a little bit different. But if we use Kepler's third law and we combine it with a derivation of Newton's law of universal gravitation, right, which was like our like g m1 m2 over r squared, okay, we actually can get this nice little formula, and I'll show you the derivation here on the whiteboard as well, because you know me, we want to use a formula, we want to derive it and see kind of where it's coming from. Okay, and basically what this is going to give us is that we can use that idea of Kepler's third law here with the whole t squared over r cubed, which will equal 4 pi squared over gms. Okay, or in this case gms, it's the mass of the sun, because we're talking about like revolving around the sun, because these would be the planets, right, revolving around the sun. But this mass here could technically be anything, the mass of whatever object you're orbiting around, right? And then this would just be a different constant if you're, say, revolving around Earth, right? The moon revolving around Earth or something like that. Okay, so let's take a look at what that derivation is going to look like. All right. So what that derivation looks like is the idea that because we've got a planet revolving around, let's say, the sun in this case, right, what's keeping it in orbit, right, is that kind of universal gravitational constant, but it's also, its centripetal force, right? It's keeping it in that kind of circular pattern. So in that case, the first thing we can actually start by saying is that our centripetal force is equal to our force of gravity, right? It's that gravity, the centripetal force is keeping it in the center, and it's that, universal gravitation that's keeping it there as well. Okay, so that's kind of our first thing that we start with. Now, we have a formula for FC. We've talked about that. That's our mv squared over r. And because this is, in space, we need to use the universal gravitation there, which is our g, and then m1, m2, all over r squared. Now what I'm going to do here for notation is I'm going to call it not necessarily mass of, I'll call it right now mass of planet and mass of sun, right? So this is going to be the mass of the planet, right? Because that's the thing that's being kept in that circular orbit. We'll say m1 here again is mass of planet, and then this is mass of sun, okay? So you'll notice that the mass of planet is on both sides, right? So that's essentially going to cancel, but what I would even do here is I would cross multiply, okay, because we know that these are equal, so it's not like a trig identity that we're trying to prove that one's equal to each other. We know that this is the case. So right now we'll set this cross multiplication up. So you got MP v squared r squared, right? So I'm doing that. And then equal here to G MP, right? Mass of planet, mass of sun, or mass of revolving object, mass of the thing that's orbiting around, right? And then times r. Right, so from there we see some things that are going to cancel, right? So we see that your mass of planets on both sides, so that can go. We say that there's an r on both sides, right? I mean, and that r is just the distance between, you know, the two objects. So obviously it's the same. So this can go along with one of these, okay? So what we're down to now at this point is v squared r is equal to g and then ms. All right, so like the mass of the sun or the mass of the thing you're revolving around, okay? At that point, we can also get v squared on its own, right? So v squared is now equal to universal gravitational constant, mass of the object that you're revolving around, divided by the radius. And then what we use here is the idea of, well, what's the velocity in question here? Well, because we're revolving around, right, and using the fact that circular velocity, right, so kind of as a side note, our circular velocity is 2 pi r over t, right? Circumference of a circle divided by the time it takes to do that entire circumference, right? So that can get substituted in for this. So I'm just going to erase and start over because I'm running out of space. This is not my ideal whiteboard, but we're making it work. Okay, so keep that in mind. We're starting with v squared equals g ms over r. And we're just going to kind of restart up here. Okay, so this is where we were at. We had v squared is equal to g mass of the sun or the thing that you're revolving around divided by r. We're making that substitution where v is equal to that 2 pi r over the time. So that's going in here for v being squared. All right, and we can then square that. And then what we get is this wonderful 4 pi squared r squared all over t squared is equal to our g ms over r, okay? And again, if we cross multiply that, what we end up getting is this 4 pi squared r cubed, right, from doing that multiplication, and then this, we get our g ms t squared. Again, Kepler's third law relates this r cubed with this t squared. So if I bring the r cubed over to that side, what we end up getting here is this 4 pi squared divided by these g ms is equal to t squared over r cubed. And that's that nice little formula you saw on the slide. Okay, that's where it's coming from. It does involve Kepler's third law, right, which is that relationship there, as well as that kind of idea of Newton's law of gravitation. Okay, so that's where it's coming from, and that is what we will use, right, to kind of determine some of these masses or periods that we're looking for, right, or even distances or anything in here that we can try and solve for. Okay, again, I know this says mass of sun in this case, but again, this mass is the mass of the object you're rotating around. Okay, when we first started the whole process, when we did like the centripetal force, right, that mass used in that formula was the mass of the object that was actually rotating. Okay, back to the slides. So that's the formula we just derived, and we're going to try and then use it. Okay, so now what we can do is we can actually use that ratio, use that formula, because it allows us to actually calculate the masses of those large planets, right, which otherwise couldn't have been calculated. Okay, so through the development of that ratio, it's allowed anyone with access to a calculator with potential to determine a very real estimate of the mass of planets in our solar system. Again, disclaimer, we know when these numbers are so massively large and we don't use one of the sig figs or we leave out one decimal place, the whole answer gets crazy off. Just as long as you're using the right formulas and the right process, that's what we're kind of aiming for here, right? Using the right science and mathematical applications. Okay, again, we've already talked about this. If we're trying to talk about calculating velocity, that's when we're going to use that formula. V is equal to 2 pi r over t, again, because it's rotating in as much of a circle as we can get, okay? So again, your radius is your distance between the two objects. Your t is your period, the amount of time it takes for one to rotate around the other one, okay? To do one full revolution around whatever it's rotating around, and then v would obviously be your speed. It would be velocity, but it's without direction, because again, if we're moving in a circular motion, our direction is always changing, but we still can have a speed, okay? All right, so here's sample problem number 1. So in this case, we are being asked to calculate the mass of the sun using Earth's orbital radius and period of revolution. All right, so we will be using that sheet that's in your formula booklets, right, that has all those constants there listed, okay? So if we look at this one with number 1, I'll switch over to the video again here now in a second. Right, we're being asked to find that mass. So here we go. Okay, so what we've got is we've got that formula that we just talked about, where we have this t squared over r cubed is equal to 4 pi squared over g, and then this was in fact mass of the sun, right, which is what we're being asked to find. Okay, now it's asking us to use, right, so these values here would be related to the thing that's revolving around, right, so this would be Earth, this is mass of sun, okay, so if we use Earth's orbital rotation, right, so t in this case would be our value if we actually look it up, right, it's on that sheet, okay, yours might be green, okay, if we look that up, right, so the period of, rotation around the sun, right, it's down at the bottom, and we get that value of 3.16 times 10 to the power of 7 seconds. You could also calculate that if you really, really wanted to, using the whole, the Earth rotates around the sun 365.25 days. So then you could take that, multiply it by 24 hours in a day, multiply it by 60 minutes in an hour, multiply by 60 seconds in a minute, right? Because your units here for t need to be in seconds. Your value here for distance and radius needs to be in meters, okay? And then obviously this will be in kilograms, and that's all because of what the units are for that constant of g. Okay, so we needed our period of rotation around the Earth. We also need the radius, again, coming from that, the radius of orbit around the sun. That value is given to us as well as 1.50 times 10 to the power of 11 meters there, okay? And then that's just a matter of being able to rearrange this formula and plugging those values in, okay? So ultimately, again, we're looking for the mass of the sun here. That's our unknown that we're looking for. So if we do a quick rearrangement of that formula, again, you could cross multiply here, right? And what you've got is t squared g mass of sun is equal to 4 pi squared r cubed, and then you're just going to divide both sides by t squared and g. So your mass of sun becomes 4 pi squared r cubed all over t squared times g, and then you're just plugging in those massive numbers. All right, so at that point, this then becomes mass of sun is equal to 4 pi squared, and then substituting in for r here is that 1.50 times 10 to the 11 meters. That needs to be cubed. It's being divided by t squared, so our t value is here, 3.16 times 10 to the 7 seconds squared, multiplied by our value of g, our gravitational constant, at that 6.67 times 10 to the negative 11 with all of the crazy units that go along with that, okay? I've done it out. It does work. The units all do cancel out appropriately. You can either believe me or you can try it yourself. And ultimately, this plugged into your calculator oh so very carefully ends up giving you an answer of, write it down, all right, plug it all in, you get that the mass of the sun ends up equaling 2.00 times 10 to the 30 kilograms, right? Or again, if you use a slightly different sig fig or decimal place, you might end up getting something like 1.98 or 1.99, okay? But both of those, that's essentially what we're looking at. So there's our mass of the sun. Okay. Okay, so there we have it. Problem number 1. Okay, so for those people who don't have access to video and they're just kind of looking at this in terms of slides, that's the answer that goes there. So again, you see that that one's a little bit different. They use a slightly different value for radius here, right? And like I said, that's off. We use 1.50 from our sheet. They're using a slightly different constant from the textbook at 1.49 times 10 to the 11. And that's where we're seeing that difference, right? But again, if we're seeing a number that's close, that would kind of round to the same thing, and you got that exponent that's at least the same, you're on the right track, okay? And I wouldn't be too particular with that. Okay, so when we talk about orbit, obviously we are talking about a controlled free fall that provides an illusion of weightlessness due to relative motion, right? So when something is in orbit, right, technically it's a bunch of different forces that are being applied to it at kind of the same time, right? You've got this centrifugal force that's kind of pulling it towards, but then it's not falling out of the sky, but it's also moving around. There's a bunch of stuff that's going on, right? But if we're going to define it exactly, it's that controlled free fall, right? Because you're falling towards whatever it is you're rotating around, but at the same time, it's in a controlled manner, right? It would give you an illusion of weightlessness due to that relative motion, right? Because you're moving around. Okay, when we talk about a geostationary orbit or a geosynchronous orbit, this is an object that makes one complete orbit in exactly the same time that the Earth rotates on its axis, so in 24 hours. So this would be something that perhaps they're using like satellites, right, where a satellite maintains its position over a certain spot of the Earth all of the time. Well, how is that happening? Because the Earth, we know, is always spinning, and what's happening is that that satellite is orbiting, right? It's doing its full complete orbit at the exact same time the Earth rotates on its axis, so that way it's always over the same spot. Okay, so again, this is what we call a geostationary or geosynchronous orbit. So that something is rotating around, the Earth in the same amount of time that it takes the Earth to spin its axis. So it's really just staying on the same spot. Okay, and all of this kind of came from this idea of Newton, which is one of his very famous experiments that we're going to kind of, well, it's a thought experiment. He never actually did it. It's something that he just thought about and then wrote about. We'll kind of spend the next couple of slides just discussing it. Okay, so Newton's hypothesis, as he was kind of discovering gravity and all that good stuff, was that if you could put a cannon, right, and shoot a cannon off the top of a mountain, if you could give the cannonball enough speed, right, and enough velocity, it would continue to just follow the curvature of the Earth, right? So, I mean, you can kind of see in this diagram here, right, if you don't give it enough speed, right, it just falls down to Earth, right, like we did with projectiles. You give it a little bit more speed, it falls farther, but again, it still falls, right? If you give it enough speed and there is no force of gravity being applied, right, you get it basically out of orbit, it's just going to take off in the direction that you shot it at, right? If there's no other forces acting, it would just go in a straight line out this way, right? But if you're able to give it just enough speed that it still kind of maintains that, it can still maintain its motion, right, but around the Earth, it would, again, just follow this path and would constantly go around the Earth, okay? That was what he kind of thought about, right? So, again, reading those notes there, right, if you could shoot a cannon off the top of a mountain in such a way that its horizontal motion would move similar to that of the curvature of the Earth, thus causing it to rotate around the Earth at a constant distance from the surface, right? So it wouldn't be falling, it would just stay in that same value, okay? So this is, again, what they termed as Newton's thought experiment, or Newton's cannon experiment, right? He wrote it in his book, A Treatise of the System of the World. And again, he visualizes that cannon on the top of a very high mountain. If there were no forces of gravitation or air resistance, the cannonball would follow a straight line away from the Earth in the direction that it was fired. If you do have gravitational forces acting on the cannonball, it's going to follow a different path depending on its initial velocity. If that speed's low, it's going to fall back to Earth. And they've actually done the math and done the calculations in terms of, well, what speed would you have to fire that cannonball out of the cannon in order for it to stay in orbit, and it's 7,900 meters per second. So a little bit nuts there, okay? So again, those calculations came from ones that we've already discussed in terms of projectiles, right? So we know that objects at rest fall 4.9 meters in the first second under the influence of gravity, right? So it's again where our acceleration of 9.81 meters per second comes from. Okay, and again, based on the size and the curvature of the Earth, Newton kind of figured out that the Earth's surface drops 4.9 meters every 8 kilometers horizontally. All right, so every time, if you were to do this whole shooting the cannonball out of the cannon here, if you shot it horizontally, right, it would fall 4.9 meters after 8 kilometers. Okay, and that would be the idea of how they've figured out all those calculations. Okay.
But what would it take to launch a cannonball into orbit? When the famous British physicist Sir Isaac Newton saw the apple fall, that some say hit him on the head, it changed the world.
You got the apple falling from the tree, and he looks up and sees the moon in orbit around the Earth, and judges that not only is the apple falling to Earth, so too is the moon.
But could the moon really be falling?
Oh!
By thinking of a cannon and the trajectory of the ball it shoots, Newton used math to unlock a cosmic mystery. It came in his landmark publication, Principia Mathematica, in 1687.
Isaac Newton has a famous drawing, and in it he draws a planet and a little mountain. There's a little projectile first kicked off the mountain, and it falls down a little bit. You give it more speed, it goes a little farther out.
Now say you could just increase the force all you wanted. It could go 50 miles, it could go 100 miles before it fell.
By adding more gunpowder, and with just the right angle of fire, a cannonball can be made to go faster and farther. Inevitably, however, gravity wins, pulling the cannonball back down to Earth.
The Earth is round and not flat, so Newton realized that if the cannonball is fired at sufficient speed, the cannonball would actually go into orbit.
For that to happen, Newton determined, the ball would need to be shot out of the cannon at 17,500 miles an hour.
It starts curving around the Earth, and he realized that there must be a speed where it goes completely around the Earth and hits you in the back of the head, never actually hitting Earth's surface. And if you duck, it'll just keep going, and lo and behold, you have an orbit.
But why doesn't the moon fall to Earth?
The moon also has some sideways motion. So for every little bit that it falls down, it also moves off in this direction, and the sum of all those motions is an orbit around the Earth.
Newton also realized that the Earth is in a giant freefall around the sun. With gravity forging the path, our planet rounds the sun like an endless cosmic roller coaster ride. Newton cracked the gravity code, and physicists are still using his ideas to solve all sorts of problems.
Okay, so I didn't realize it was going to start right before I could kind of give you a heads up, but again, that's kind of a better explanation probably than what I could give you about, Newton's cannon experiment and all that kind of stuff, and kind of better visualizations, but there you have it, okay? All right, so let's kind of take a look at that idea of geostationary orbit then, right? So so something that's actually rotating around the Earth but seems to stay in the same spot, okay? So again, it kind of uses that idea that we've already talked about with that whole Fc equaling Fg, right? The centripetal force being the force of gravity, okay? And being able to use that formula that we've seen. Okay, and again, that's that same idea that geostationary orbit can be used to find the mass of other satellites or other objects, okay, or also being able to calculate the radius, right? How far away is something rotating around? How far away is it from it for it to stay in orbit, okay? So using a slightly different version of, the same one actually, I know this sounds terrible, but I'm not fully going to derive this one, per se, but we can use the following formula, right? So this is for geostationary orbits, right? So 4 pi squared r m naught, right? So m naught being like the object, or mo, I guess, the object that's in orbit, and then your gmp equaling mo, so like your p being the mass of the planet that you're, orbiting around, right? So those would be the notations that we're going to use there. Right? So that's kind of our lovely little formula that we have. Okay, so that's what we're going to use for our geostationary orbit formula. So we'll look at this sample problem here. So it's asking us what altitude is required for a geosynchronous orbit. Now I lied, I said I wasn't going to derive this, but I am actually going to slightly show you where that's going to come from, and it's going to come real quick. So let's just kind of take a look at that. Okay, so again, it's that idea of force of gravity, force centripetal force equaling that force of gravity, right? And if you remember, we looked at two different formulas for centripetal force. One was mv squared over r, right? But the other one was, if you look at your formula sheets again, was this 4 pi squared mr all over t squared. That was another definition we had for the force of gravity. And again, because this is in space, we're using that gravitational constant here of m1 or m object orbiting, and then mass of planet over r squared. And again, this case, this is again the object that is actually orbiting around. So that is over there. Okay. So this is kind of the formula then that we can use, right? That's the one that was on the slide, and that's where it's coming from. It's just coming from this direct FC equaling FG. All right, so the question itself was asking about, I'm gonna have to go back and look at it again. Altitude is required for the geosynchronous orbit, okay? And we are assuming that in this case it is going around the Earth, okay? So things that we're gonna need to know then, right? We are going to need to figure out a couple things. One, we do see that the mass of the object will cancel out from this formula, so we don't need the actual mass of the satellite or whatever the object is, right? So really, we're just looking at this formula instead, right? So again, if we kind of cross multiply here, we get this 4 pi squared r cubed here equaling our g mass of planet t squared. Okay, the thing that's going to help us find that distance is r. However, remembering that r is the distance between the center of the Earth and the actual object itself. So remember, when we go to find that, we're then going to have to subtract the radius of the Earth to actually get the height of the orbiting object itself. Okay, so just kind of keep that in mind as we kind of work through this a little bit. Okay, so g is a constant, we have that. What we're going to need is the mass of the planet. So in this case, we're thinking about Earth, in this case, right? So that has a mass, put that in. Our mass of our planet Earth in this case is our 5.98 times 10 to the 24 kilogram. Okay, our value of t, right? So again, what we're talking about here is what's happening with the satellite. It's rotating around the Earth at the same time it takes for the Earth to do one complete axis. And that's 24 hours. But we need to convert that 24 hours into seconds. So it's that idea of 24 times 60 times 60. So our value of t here is going to get used at 86,400. Right, and that's seconds, and that's going to get squared. Okay, and then our radius is what we're going to solve for. So all I need to do now, take that r cubed, and I'll divide this by my 4 pi squared. Okay, so again, plugging all of that in and using our 6.67 times 10 to the negative 11 here for g, that gives us an r cubed value here of 7.542 times 10 to the 22, and that ends up units-wise being meters cubed, which then we would cube root, right? This is r cubed. We'll want to cube root that, and when we cube root that, right, so you're doing this, so that cancels, you're cube rooting this, so that cancels well, it doesn't cancel, but you're cube rooting it to give you a value here now of essentially it's 42,250,474.31 meters. Okay, but now that is the radius from the center of the Earth to the actual orbiting object, so the satellite itself. So we have to now remember, okay, well, what's the height of the actual, like what height above the Earth is the object in geostationary or geosynchronous orbit? So from this, we now need to subtract the radius of the Earth, right? And again, that's a constant. So let's, again, wipe this clean and do that calculation. Right, so we have again from our constants that the radius of the Earth is a value of 6.38 times 10 to the power of 6 meters. We just had that value of the distance between the center of the Earth to the actual satellite, right? Was that 42,250,473. So our altitude of the satellite itself will be that value that we calculated previously, right? That let's just change it to sig figs or scientific notation. Sorry, so let's say 4.225 times 10 to the 7, right? Minus that radius of the Earth, right? And you get a value here once we subtract those things to be 3.59 times 10 to the 7 meters. All right, so that's going to end up being the height of our satellite required in order to stay in orbit there. So there you have it. Okay, and again, there's like a full solution there. You see slightly different values again used in that particular solution. I might fix that slide and post the other one. Oh no, pretty close. Yeah, no, it's actually the same, right? So 3.59, it's down there. Right, yeah, so 3.59 times 10 to the 7 meters, or that same idea of dividing that by 1,000 and getting 35,900 kilometers. Okay, so this would be where I would typically say, okay, do a practice problem, we'll go over it. We're just going to go over this one again as part of this video, and then you will have 4-ish textbook problems to work on. I will quickly need to go and double check what those numbers are. I forgot to change them into what they are in your textbook, but I will do that for you, so don't worry about that. But let's take a look at this final practice problem here. Okay, so in this one, we've got certain weather satellites that orbit Earth every 90 minutes. How far above the Earth's surface is their orbit? Remember that the center of the orbit is the center of the Earth, right? So it's that same idea. Okay, now if you want, by all means, pause this video, try and figure this out without having me do it. But other than that, I will just go through this one again, just give you another example of what we can use here. Okay. All right, so again, with this one, we're being given that the time that the weather satellite orbits the Earth, it does it every 90 minutes. We need that in seconds, so just take that and multiply it by 60, and you get your 5,400 seconds. Okay, the mass of the object, we don't know how big the satellite is, but we don't actually need to know it. We do know that the mass of the Earth, right, the object that we are orbiting around, we have that value here, and that value is 5.98 times 10 to the 24 kilograms. We also have that the radius of the Earth itself, which is something we're not going to use in the question. It's going to be similar to what we did previously, but we're going to need to use it. But that value is another constant of 6.38 times 10 to the 6 meters. All right, so again, we're using that same formula with the FC equaling FG, and using that version of the formula where it's 4 pi squared mass of the object, right, times the radius divided by t squared is equal to gravitational constant, mass of the object, mass of the thing that you're rotating around, planet, in this case, Earth, right? So I'll actually put that as E, because we are rotating around Earth there, all over r squared, okay? We are solving for r in this case, so again, it would be like a, let's cross multiply here. We see that these would cancel from both sides, and what you'd end up getting is, again, it's the same cross multiplication formula here, right here and here. So you get that 4 pi squared r cubed is equal to g me t squared. We're solving for r, so we're going to divide both sides by 4 pi squared. So r cubed is going to equal g times the mass of the Earth, which was here at our 5.98 times 10 to the 24 kilograms, times our time. Again, this is the time of the object that's orbiting, that's in geosynchronous orbit, so that's 5,400 seconds squared. And all of that would then be divided by 4 pi squared. Right? And then again, you're using g here as your 6.67 times 10 to the negative 11, and all of the crazy p units that go after it. And then once you get that value, which we'll do up again here, you'd have to cube root it, right? So plugging all of these numbers in, again, very, very carefully into your calculator. Use as many brackets as you need to, or do it in as many steps as you need to so that it's right. You then get this idea where we get that r cubed has a numerical value of 2.946 times 10 to the 20 meters cubed. You cube root both sides, right? That cancels, and you get a value for r as 6654032.74 meters, or if you want to go back into sig or scientific notation, it's 6.654 times 10 to the 6, right? 1, 2, 3, 4, 5, 6, just as a quick recap there. Right, so that's the radius of, so the distance between the center of the Earth and the weather satellite that's orbiting, and then you would just need to subtract, right? So the altitude is going to equal that value of r minus the radius of the Earth itself, right? So that would be that 6.654 times 10 to the 6 minus our radius of the Earth, which we had listed as 6.38 times 10 to the 6, and you do that subtraction, and you get this value of 2.74 times 10 to the 5 meters, or again, you could divide that by 1,000 and get something in terms of kilometers. Okay, and that's where, again, so again, you see something slightly different as the answer that somebody had here, probably from the back of the textbook, 2.70. Again, I could have probably kept more sig figs in my solution, or used a slightly different constant for radius or radius of the Earth or mass of the Earth, right? So that would just change things just enough. That would be a little bit off, but again, same ballpark, still around that 2.7, still the same exponent there, okay? So again, these are your independent practice problems. These are from the textbook. If you did not bring your textbook home with you, please shoot me an email. I do have a PDF version of the textbook. It's this textbook, so then the PDF version would always have these right page numbers with these right numbers, but let me just quickly go grab my textbook, and then I will give you the correct page numbers because I forgot to change that. So 1 second. Okay, so the actual numbers that you are wanting to look at here are from chapter 12 in universal gravitation, and page number would be 586 is actually what you're going to be looking at in your textbook, and the questions themselves are actually the same in terms of numbers, right? It is still 9, 10, 12, and 13. You'll notice that 11 in the textbook is the one that we just did as a sample problem anyway. Okay, so those would be the questions. Those are your quick answers, but I will also post the full solutions of ones that I've already got worked out and done. I'll post those as well, so that if you're getting stuck on something or you want to see if you maybe potentially made a mistake, what you need to do for that. Okay, so that's that. I will try to get better at this as we go, but this is kind of what we got for now. So hopefully that's something. Again, you can rewatch the video or you can just look at the slides. And you'll just do those textbook questions, and then I'll have another video for the next stuff. And I won't ask you to submit all of your textbook questions. It will just be more along the lines of, hey, are you kind of keeping up with the work? And every few classes I'll give you something to kind of do as a check-in that you'll send in and I can try and mark for you. All right, and we'll kind of adapt as we go. Okay, that's it.